crystals until July, 11th of July? Yeah, until the middle of July. Okay, so afterwards, yeah, perfect.
Welcome everyone. It's a pleasure to have with us Luiza Angheluta. She comes from the University of Oslo. Luiza comes originally from Romania, but she did her master in the Niels Bohr Institute in Copenhagen in 2006, and then she moved to Norway, to Oslo, to do a PhD in the University of Oslo under the supervision of Joachim Mathielsen. And then she's now associate professor there, and she has made some stays abroad. For example, she has worked with Nigel Goldenfeld in Chicago, and also she was visiting us 2 years ago, I think. Seminar, and she's interested in many topics related to vortices, defects, its many contexts, for example, in two-dimensional turbulence, in quantum and classical turbulence, and also in defects in materials. That is the topic that she will be talking about today. And you see this work is made in collaboration with some good friend of some of us, Cotopiñán. So let's see what you have to say.
Thank you, Emilio. First of all, I'd like to thank the Institute for the great opportunity, giving me the opportunity to be here for 2 months. I definitely enjoy my time so far and have great conversations with many of you. What I'm going to talk to you about today is this recent work done together with Evinance, whom some of you are quite familiar with, and together with my PhD student, Audun Skaugen, from the University of Oslo. And the topic is to study defects in crystalline materials. And I'm going to tell you first a little bit of the motivation and how we come to this problem. It relates to crystalline structures of being omnipresent at all scales in very many different systems, starting from the classical one with ice, rocks, metals. And it has practical applications, first to understand the large-scale behavior of glaciers and ice in general. It's related, the defects are related a lot to detailed processes that happen in the rock deformations. So for geoscience, it's very important to understand microstructures. Material science, metallurgy, and all of that are very much interested in quenching alloys and controlling the material properties, you know. But of course, with the incent of nanotechnologies and scaling down to the devices to nanoscale, there's the emergence of new materials that have crystalline structures at a certain scale, or properties that are on a lattice. For example, the liquid crystals, the so-called material by design, or this architectural structures where you try to defy the correlation between the density of the material and the strength of it by constructing this architectural materials where most of the material is made of holes, but then you have this skeletons that sustain all of the material weight. And then, of course, you have the new technology around photonic crystals, which are which are also present in nature in many animals. They show colors not by pigmentation, but by this photonic crystal, which is to say that the underlying material has this periodicity in the refraction indices. We have experts here that can tell us more about this. But anyway, the point is that we see crystalline structures in very many different cases, and there's a correlation between the underlying microstructure, in this case on a lattice, and the macroscopic properties. And here I'll be focusing mostly on the mechanical properties, but one can also be interested in the magnetic properties, optic properties, and all the other things. And what happens when you have defects into this microstructure? How will that affect the microscopic properties? Okay, that's one motivation. In particular, when we are looking at the mechanical properties for this crystalline materials, but in general for all materials, there seems to be different stages of deformation. So if you would plot the deformation in this axis where the vertical one, is this? Okay. So this corresponds to the force field per unit area is like the stress, and this is the response measured in terms of the strain, okay, the relative deformation. You would have the regime of linear elasticity at the for very small applied forces. You have this linear response, the elastic spring, right? But as you increase the applied stress, you enter into this nonlinear regime, which is also called the plasticity regime. It's dissipative, it's irreversible, unlike the elasticity regime, and eventually it leads to breaking of the material, failure. This is a curve that most of the time is represented on a macroscopic material, but when you go down to scale and you have a lot of defects, it turns out that this stress-strain curve, it's not unique. It's not unique to the material. Even for the same material, you can obtain different stress-strain curve depending on the system size, the detailed microstructures in that particular sample, and so on and so forth. So this is an example where when you zoom down, you start to see defects. They're called, well, there's different kinds of defects that appear there. The ones that we're going to be focusing on, they're called dislocations. And you have a bunch of them when you go down to microscale, and when you reach the millimeter scale and larger, you create grain boundaries and polycrystalline structure, and eventually you lose the lattice symmetry, and the material becomes continuous or uniform. So there is this theoretical challenge, fundamental challenge, to relate the macroscale deformation to the macroscale properties that we're interested in, and how do they couple with the lattice defect, this bridging of scale, this interesting multi-scale physics is the one that poses fundamental challenges. And of course, there's many approaches depending on the community. In material science, there's a lot of theoretical effort in this case, but also in statistical physics, it becomes more and more fashionable to study these problems, as I will explain to you, because it has signatures of phase transition. But you see here that there's different kinds of modeling approaches, different kinds of experimental approaches. And I like this quotation. They're all basically wrong, but to some extent useful, depending on the question that you're asking. So we're going to propose another kind of model that is going to come somewhere around here. It's a phenomenological mesoscale model, but all of this are phenomenological at a certain level, and that's the part that is arguable, right? But the question is at which level you put the phenomenological inputs, because what you put in is somehow related to what comes out. So I'm going to come back to that point. So in particular, if we think about single crystals, then the kind of defects that we're looking at are these dislocations, and they sometimes, you can have a gas of dislocations, but they are not, the system is not sufficiently big so they can pile up into grain boundaries and break the crystal into subcrystals. So they are still sort of like a interacting gas of particles. And in this case, the stress-strain curve has this signature that when we enter the nonlinear dissipative regime, the curve loses its smoothness. It becomes sort of fluctuating, so there's strong fluctuations that appear in the response, and then eventually you get into the plastic flow regime. And these fluctuations, this bursts in the strain response, have power law distributions. They're broadly distributed. That means that all the local averages approaches fail in this regime. You have to worry about correlations in the system, so you have to worry about non-local effects and how to put them into the theory. And the second interesting effect that emerges when you go to small crystals on the order of microscale and below is this effect of smaller gets stronger. That is this yield point, this transition from a strain rate independent to a strain rate dependent. So here is time independent deformation, here is time dependent, like a viscous flow. So this transition is called the yield point, and this transition stress, I plotted this the other way around. Yes, should increase with the system size, right? Should increase with decreasing system size. Smaller gets stronger. Okay. I'll show you the experimental data where it's correct. So here is the experimental data collapsed onto a log-log plot to show the emergence of this power law with an exponent that we don't understand. We don't know, but it seems to be quite robust. And you can see it here on a particular example where you apply a compression on a nanopillar, and then eventually at the end of the experiment it's broken and it has the shear bands. But in between, when you measure the strain and you plot it in this curve, you see that it gets very, you have this strain bursts, but the yield point is increasing with decreasing the diameter of the nanopillar. All right? And the strain burst, as I said before, seems to have power law distributions with an exponent that fluctuates around 1.5. So it started with the 1.5 avalanche statistics, earthquake-like events in single crystals, but then it turned out that there is quite a bit of variation around that exponent, and we don't understand why is that. Why is there power law? So there's a lot of open questions. And of course, if you go to higher scale, then you start to worry about the grain boundary and in polycrystalline materials. And there's two new pieces of physics that come into the game. One is the effect of the grain boundary that acts like a barrier to dislocation motion. So they can't go too fast because then they get absorbed to the boundary, they interact with the boundary. And then there's also a finite size effect when it comes to the statistics. And that introduces a new level of complexity. So this is just the sort of overall motivation for the talk. Now we're coming to the part where I'm going to present the model. And we're not really addressing any of this, so this is like in the future to be tackled. But we need to have a robust model that we believe in, and we think we can push it to really give us quantitative analysis of these regimes that I just presented to you. Okay? So it's a matter of where you put the input variables in the system, at which level of description. So I'm going to present to you this faithful crystal model that has been around for a while, but we have taken a new interpretation of it and derived a mesoscale stress, microscale and mesostress stress field that it's going to be like our stress observable. Okay, so we can calculate all of the stress strain curve based on this stress field. We show that it has all the properties that are interested to be a mechanical stress. And then we're going to discuss, these are equilibrium properties, but then we're going to get into the non-equilibrium properties and the motion of the defects, what drives the motion of the dislocation in the stress field and in this lattice, and how do they interact with each other. Okay? So let me start with the very microscopic description that some of you might be familiar with, and how do we coarse-grain it to the mesoscale and introduce this faithful crystal model. So at the almost atomic scale, one can construct a model of colloidal particles where you have individual particles satisfying the Newton's law with some thermal fluctuations, or not necessarily thermal, but there is some sort of random noise associated to them. And then they interact with each other through an interaction potential, so that when we twin the interactions between them, we can go from a gas to a crystal that eventually crystallizes and spans the whole system, right? Now we want to coarse-grain the system, so we introduce this single particle density that is not average over the noise to start with. Yeah? And then, I'm not going to go through the details, but there's a standard procedure that takes you from this Langevin equation to the coarse-grained Dinh-Kawasaki-like equation, okay? Where there is the appearance of a multiplicative noise that is related to the intrinsic noise of the colloidal particle, right? And then there is a coarse-grained and effective Hamiltonian that is related to that has a local term, which is related to the diffusion in this case, and a non-local term related to the interactions between the particles, okay? The problem is when we try to average over the noise, then this equation becomes non-closed. So we have the closure problem in the sense that the one particle statistic depends on the 2-point statistics, and so on and so forth. So you need some sort of closure approximations to actually deal with this, to actually deal with these equations. And that's the level of phenomenological input where you say, well, I work in the low density expansion. I can just say that I can write this as a product of the 1 point density. I work in the low density uncorrelated limit, okay? Or you can have another approach, which is called the classical density functional theory, where you replace this term here with something else. So first you look at the density fluctuation relative to a reference density. In this case, it's the uniform liquid phase, okay? And you look at the density perturbation around the uniform liquid phase, and you write the evolution equation in terms of this, for this density perturbation, psi. And then there's going to be this coupling that appears in here. And now I can do this decomposition at some level. I get rid of the, well, I think there was another approximation here that the interaction potential is all buried in the pair correlation functions for the equilibrium, okay? And then if you have an input of this pair correlation function for the equilibrium liquid, you can somehow can model this, dynamics also outside of the liquid phase. So you can model crystallization by just inputting the pair correlation function for the liquid phase, okay? Now, how do we get to the phase-field crystal is to look at the structure function, which is the Fourier transform of the pair correlation function, okay, for a typical liquid. And then we do a gradient expansion. So we do basically, in the Fourier space, we do an expansion around the maximum, because the maximum is going to give us the perfect order, and then you have the perturbation from the disorder, right? And so if I just expand around the maximum to the fourth order, I can then reconstruct a correlation function that has some sort of a gradient, has some sort of a non-local term that is a gradient term, right? But then it also has a delta function that is located around the peak. Okay, so we turn this absolutely non-local field theory into something that is also non-local but has a gradient. It's called the gradient expansion. All right, and this is going to model. And then the local term has different variants. I can just keep the logarithm, or I can also expand the logarithm around the equilibrium state, and I get the double well potential. So I know that I have a phase transition from a state that is uniform to potentially a state that has different symmetries. Okay, so if I calculate the phase diagram for this particular free energy, actually we see that it has a constant phase related to the equilibrium liquid, so there's no structure. And then depending on the quenching depth and the mean density, we can either have a crystal phase or a laminar phase. And there's also coexistent boundaries between them. All right? This has been the model proposed over a decade ago as a very nice phenomenological model for crystallization processes, anything related to liquid crystal phase transitions, and also crystal behavior. All right? But this is where it becomes phenomenological, because there is this step that you go from the correlation function to the gradient, and you have this gradient expansion. Everything else is supposed to be derived from this. So if you believe this phenomenological free energy, everything else comes as a consequence of this setup, right? So this is the level of we have a phenomenological free energy, and then the rest follows from that. But it might relate to your work by a different kind of free energy. Maybe it's a more ab initio free energy. But if it can capture this symmetry phase, then we can relate it to some derived, we can propose some derived quantities from that free energy, okay? So in particular, let's focus on the, oh, okay, I still have some time. We can focus on the crystals, the equilibrium crystals in 2 dimensions. So by minimizing this free energy at a given fixed density, we can get a hexagonal pattern. In 3D, it will be BCC patterns. Depending on how you can tune this this non-local term, and you can add another combination of higher order gradients to build up different kinds of symmetry. You can also have a cubic lattice in 2 dimensions if that's what you want. So there's a certain degree of freedom to play with this non-local term. But the point is that you have a crystalline structure by whatever means you want to derive it. All right. So at equilibrium, then this density field, which is also like an order parameter for the defects that we're going to study, in the one-mode approximation can be considered as a superposition of three waves with these wave numbers, wave vectors, and with an amplitude that is given by the quenching depth and the fixed density. And it's taken out from the stability phase that we had before, okay? In addition to that, we want to now construct, so this is basically the only variable that comes in this description, then the density. But the thing that we've been discussing is that if you want to study mechanical properties, just having the order parameter as the only variable in the system might not be enough. So we might need to decouple the dynamics of the order parameter from the dynamics of momentum. So how do you conserve momentum and mass only with a mass conservation law? That's the fundamental question. We need another variable. And that we do by defining.
So why do we need three vectors?
Oh, because we have this hexagonal lattice that is made of these three plane waves, basic plane waves. Well, actually, they're not. You just need two. The third one just comes. Yeah, that's true. That's true. I just wrote this three for this three, but only if you just have two, the third one comes out. That's true. Hmm?
You need to superpose three to get the shape.
Yeah, to get the what's it called, the resonance. To get the resonance condition, you have all three of them.
The fixed direction which you
Yeah, that's true. Okay, so now in order to study mechanical deformation, we have to think of deformation. How do we apply a deformation field? So we start with a simple case where we have an affine deformation U that gives us that takes us from an unperturbed system to a deformed system. This is the case where I just apply a shear in one direction. Okay, but it's a smooth deformation and it's small. So the gradient of this deformation field is assumed to be quite small. So we are in the regime of linear elasticity. Okay, so if we do now a variation of this free energy with respect to changes, variational changes in this deformation field, we can derive this expression that looks very much like the linear elasticity. Okay, so that leads us to the definition of a microscopic stress field. There's a little bit of variational calculus involved in it, nothing complicated, but kind of technical. But the point is that you can carry out those differential partial derivatives, and you can calculate a macroscopic stress field from the form of the free energy. So if you have a free energy, that's different. Okay, so this term here comes exactly from the gradient expansion. If I had from the gradient expansion, yeah. If I had another no local term, it would come up differently. Okay, but for this particular form of the free energy that we are using, we can derive a microscopic stress. So if I plot the stress here, you can see that it actually acted at the level of these individual atoms, right? And it oscillates at the level of the lattice. However, if I coarse-grain it, if I average it over a lattice unit, I can produce a uniform field that is smooth on scales larger than the unit lattice. So this field can be used to couple the microscale with the macroscale because it's continuous. Okay, so it leads me into the continuous elasticity theory. So in order to show this, for example, we can use the one-mode approximation where we distort the phase field density, this order parameter, by applying a smooth deformation field in the phase. Okay, and if we carry out this expansion into the definition of the stress field and average over the unit cell, we end up exactly to the linear elasticity rheology, like a relationship between the stress and the strain. And in particular, all of these coefficients, the Lamé coefficients, are directly related to the equilibrium amplitude. So they depend, so the elasticity coefficients depend on the quenching depth and the density that we're fixing. And at equilibrium, this directly translates to elastic equilibrium, mechanical equilibrium. So the gradient of the stress, which is the force, equal to 0. All right? So this seems to be like a very suitable candidate for calculating mechanical properties, right? I have a way of extracting the stress. If I deform the material, I know how to calculate the stress. Or if I fix the stress, I know how to calculate the deformation field. So I know how to extract mechanical observables just from a density field, which before it was a little bit more ambiguous. How do you define those? But does this work also in the presence of defects? Okay, so let me tell you a little bit about the defects in the crystals and how they are related to topological defects, and that they actually are stress localizers for this particular definition of the stress field. So let's go back to classical elasticity, where a dislocation is defined as a singularity in the mechanical response. In this case, if you look at the stress fields in linear elasticity, you have a singular behavior. So the stress field diverges at the dislocation, but also it has it's also asymmetric. So for example, if you look at the compression stress, sigma xs, it has a compressional stress here above it, and it has a extension negative stress below it. So the definition of an edge dislocation is that you insert an extra plane somewhere. And it's a topological defect because all the affine transformation that before you could do no longer hold. So for example, it's the same as with the vortex in a field. So if you do a loop, if you do a contour integral around the dislocation, no matter how far away the contour is, you're going to pick up a phase. Okay? So it's not going to be equal to 0 as it would be for an affine transformation. So in this case, for example, if we start here and we make a loop around it, and I want to go 4 lattice sites this way, and I also want to go 4 lattice sites the other way, you see that there is a gap. I can never close the loop. I come up with something, and that's what's called the Berg effect. Okay, so unlike for vortices where the charge is actually a phase, so it's a scalar. For vortices, the charge of the vortex is a vector. So it tells you the amount in lattice units that you need to have in order to close the loop. Okay? So mathematically, if you have this deformation field, yeah, and you do a loop around the deformation field, if that loop has a dislocation in it, it's going to pick up, it's going to be non-zero, and the value of this contour integral is directly related to the Berg effect. Okay? So that's the definition of a topological defect, because it's a local tier, it has topological properties. So do we see the same thing in our model? That's the question. And we do.
Luiza,
yeah.
U was the odd deformation. It's something that you were adding on it. While here it seems it's something that you are measuring when you defect this spread. I don't understand.
That's true. That's true. So in order to derive the stress, we used an affine transformation in post stress, but here it's an internally induced one. But the stress can still be applied. You can still have the same definition of the stress. It still works. Yeah, but it's true. This deformation field doesn't need to be imposed by the external field. It just comes just because you have a dislocation. That's why dislocations, they localize deformation. So even if there was no deformation there, if you have a defect, it will localize deformation. It will produce deformation, but it's also localized. So in the phaseful crystal, we have a dislocation in this case, and it's a little bit more complicated in the sense that we insert 2 planes. You see the planes coming up here, and then on the other side they are disappearing. So we have this 2 extra planes that are inserted up to this point and not beyond. So that means that we're going to have a compression stress here and an extension stress there. The signs are also maybe different. Yeah, no, it's correct. So there's a compression stress here and an extension stress there. All right? And you can also look at the shear stress, and you see this this shape here. But if you look at the microscopic stress, you see that it kind of localizes the stress. You see that there's something going on here, but because of this microscopic oscillations, it's hard to see what's going on, right? It's hard to visualize the stress localization, but definitely upon coarse-graining, they come out very nicely. Okay, it's not a true singularity, as we will see, because this defect, because this order parameter is smoothed. So we are at the scale where we cannot really have a singularity. But if you coarse-graining all the way into the continuum, they will appear as singularities. But at this mesoscale, there is no singularity. So that is to say that the dislocations have a finite core. Okay? If you shrink the core to 0, then it becomes a true singularity. You can also consider the case of two dislocations in two glide planes, and you can have this quadrupole shear stress. And what's the relation to the topological defects is that in the one-mode approximation, when we write the order parameter, we expand it in terms of these three amplitudes. If you look at the magnitude, it's a complex magnitude when you have a defect. And those three magnitudes are going to be so that one of them is actually continuous, and there's no discontinuity next to the dislocation. But for the other two, we see in this particular case where we have two dipoles in two parallel glide planes, we see that there's two waves that have a topological defect in them. All right, they come up and then you can see very nicely the phase singularity. And you can see that the magnitude goes to 0 while the phase becomes singular. So they are topological defects. So now how do we relate the Berger vector that we see in the hexagonal lattice to the topological defects, topological charge of the amplitudes? And the mathematical relation is through Mazenko's transformation, which is a very nice transformation when you have an order parameter and you have a symmetry breaking and you produce topological defects. You can locate the position in the real space of those defects through the zeros of the order parameter. So you go from the 0 of the order parameter to the location of the defect. And then this Dn is the Jacobian transformation matrix. So n is a complex variable. It has two functions, right? And r is a number, is a vector in the plane. So you have a 2x2 matrix, which becomes like this in 2 dimensions. Of course, it's a little bit more complicated if you have an order parameter in 3 dimensions, and the intrinsic order dimension of the order parameter is different. But even in that case, Mazenko has shown that you can still have a transformation from the defects to the zeros of the order parameter. Okay. So this allowed us to then define the Berger vector in the hexagonal matrix through this combination of the wave numbers and the zeros in each of these waves and the Jacobian transformation matrix. And it works. It works. You can calculate, I haven't shown it here, but if you calculate the Berger vector, you can actually get the Berger vector density field, which is, again, this is a continuous variable here. We have coarse-grained, and you can enter this into continuum models. But it comes directly from the microstructures. This is the important thing. How does this work when we have dynamical properties? So far what I've shown is for the case where there's no dynamics. Now, when we put in dynamics, basically this order parameter field, this density field, has a diffusive relaxation dynamics, right, towards whatever equilibrium it can reach, right? So it has an equation of this form. And what we have been able to show is that when you have this equation only for the order parameter without constraining the stress field is not going to follow the mechanical equilibrium. So the stress is also going to evolve, which means that when you think about the mechanical properties, they are going to be dependent on the evolution of the density field. So it's a little bit of a mixed situation, because from the conservation law, we only have conservation of mass, but then you want to get the momentum conservation, and you want to get all the other conservation law just from this one. So you couple them together. So you have a complicated material response. So in order to separate between them, you need to introduce an additional field that constrains this mechanical equilibrium. But it turns out that even if you just solve this equation, it's a very simple description that can capture, at least at the phenomenological level, quite a bit of crystallization phenomena. And it has been used extensively over the past decades to study all kinds of crystal-related phenomena. For example, this crystallization, that you actually start with a seed with different lattice orientation, and you can see that if you start in the phase space where the liquid is metastable, then this crystal is going to grow, and you can even have faceted growth, and you can have dendrite growth. You can see the snowflakes, but when they are close to each other, they're going to form grain boundaries, and then you get into this polycrystalline coarse graining, and you can study coarse graining dynamics and all kinds of stuff. So in particular, for a bigger system, you can have a map of the orientation, grain orientation, and you can see that at the beginning you start with a lot of small grains, but when you let the system evolve, you eventually go into larger and larger grains. It's called coarse-graining process. And if you calculate the average area of the grain as a function of time, you see that it's growing with time. And at low quenches, so that is close to the critical point, you see that it has the normal growth, which is basically driven by the surface energy, if you want to think of it. But when you go to deeper quenches, you have this anomalous growth that it's poorly understood, but it's observed in molecular dynamic simulation, is observed in experiments. And there's various theories related to this slower coarsening behavior. One particular mechanism that we have studied is this grain rotation and the grain stagnation. That if you quench the system even further, this coarsening is going to stop. So you cannot really go directly to the homogeneous state. The material is going to be metastable for a very, very long time with the grains. You cannot get rid of the grains. So in processes like epitaxial growth or like other processes where you want to control the microstructure, depending on the temperature that you are working on, it might be very difficult to get rid of it. And this is quite nicely captured in this thing. And you can also study the defect dynamics. You can see that in a single crystal they can move around, and sometimes they can form this transient domain walls like grain boundaries. So when they are trapped together in a grain boundary, they move much less. They kind of jiggle around to the mean velocity of the grain, whereas when they are isolated, they can just move with the Rayleigh speed. Okay. So the message is that this diffusive dynamics can produce topological defects. They can do a lot of stuff together, so it definitely gives you some sort of material response, because if the defects are moving around, that means that the material is deforming, is flowing, whatever, I don't know, is doing something. But it's only doing because the density is having this diffusive dynamics. There's no other constraint. And so the question is, if these defects are created by the diffusive dynamics, what drives the motion of the defects? Okay, how are they created and what drives the motion of them? And so we've been investigating this also in the spirit of topological defects and localizing topological defects as the zeros of the order parameter. And what we found out is that the velocity of the defect is directly related to the stress. And in certain limit is like the Peach-Koehler force. So the velocities, so these defects, they live in a stress field induced by the other defect. Each dislocation produces a stress field, and the dislocation interact with each other through the stress field. The question is if the stress field is at equilibrium or not. Is this an elastic stress, or is it a much more complicated stress? All right, so because these vortices in the amplitude expansion are topological defects, they satisfy a conservation law. They always come in pair, they always annihilate in pair. So there is this basic conservation law of the charge density field. With the current, that is directly related to the evolution of the amplitude and some spatial derivative in this combination. Okay? So this is something that has been calculated by Musenko. It's a technical calculation, but let's just say that it's a formula like this. We know it. Then how do we translate this for the Berger vector? So that means that the Berger vector also has a continuity equation. That is, again, in the absence of external forces, right? There's no external force that I have applied here. Everything is just, I don't know, crystal growth. There's a spontaneous fluctuation that produces this defect, and then they just satisfy this continuity equation. Okay, this is conservation law. With this current, now it's a tensor field that is related to the current in each of these amplitudes that carry a topological defect and the wave number with this particular definition. If we use this definition before, well, there's a couple of steps, but basically it can also be written like this. Now, if I substitute the zeros of the order parameter through the Mazenko transformation, I can relate it to the location of the dislocations and the Jacobian of the transformation. So then we have this expression for the current associated to the Berger vector. But this current can also be written as an advection current. So if I have a dislocation that is moving with a certain velocity, the dislocation is at position r0, it moves with a velocity v, and it has a Berger vector b, then I can construct this, by definition, this current that it carries. So by just identifying these two expressions, then we can predict what is the velocity of the dislocation directly from the evolution of the phase field. So again, we just have a density field that has a periodic structure in it, and the periodic structure carries elasticity with it, and with elasticity also singularities in this elastic field. And the singularities move through the interaction with each other, and we can calculate the velocity of the singularities from the dynamics of this periodic field. I think that's quite neat. So now, in a particular situation where we have some simplification and we assume that the system is infinite and we can approximate this equation, is quite complicated because it has nonlinearities. But if we ignore all the nonlinearities, the time-dependent evolution of the density field maps into an evolution equation for the amplitude. And next to the defect, I can just look only at the linear part, and all the other terms are going to be equal to 0 because close to the defect, the amplitude goes to 0. So I can use the linearized approximation and say that to the leading order, it's driven by this gradient operator, which means that if I now say that this dislocation lives in an applied field, this applied field could be imposed by the external boundary condition or by the fact that there's another dislocation somewhere else, right? So if this dislocation is by its own in an infinite field, by definition, it's not going to do anything. It's going to be static. But if I apply a force, it's going to move under the influence of that force, right? And so now I'm applying a smooth force, and what we show that it's within the linear regime, the current of the order parameter is directly related to the gradient of the applied field. And as a consequence, when we carry all of this machinery, the velocity field is also going to be proportional to this gradient field. And we know from from what I've shown before that the gradient field is linearly related to this stress field. So basically, the velocity is directly proportional to the it's related to the stress field and the Berger vector. Yeah, and this expression is precisely the Peach-Koehler force. In 3 dimensions, it's a little bit more complicated, but in 2 dimensions, this is the expression. And the interesting thing is that the mobility that we can predict within this approximation is the same, both if the velocity has this climb motion or this glide motion. So I didn't talk about this, but basically when we have these locations in a hexagonal structure, they can either go, what can I show you? Here. So you have this dislocation here. It can either glide along the Blaise plane, it has one velocity, but you see it can also move this way, in this direction, and that's climb. And this direction, it's typically, it requires an energy barrier. So at high temperature, it can come up, but at low temperature, it's mostly glide motion that comes up. But when we are close to the critical point, this is the regime in which the amplitude expansion that we have been using mathematically is strictly valid, then both motions are allowed. And so you could see both the climb and the glide. And in that case, we predict that the mobilities are the same. But in reality, they're not the same. So the mobility for the climb motion, it's very much dependent on the temperature, and it's going to be very much reduced at low temperatures. Okay? So of course, analytically, we're in a restrictive regime, but nonetheless, numerically, we still have a reliable way in which we can calculate them, even at deeper quenches. So this formula is not going to be valid everywhere, but the basic formula that we are using, we have shown that it actually works also in lower quenches. So let me tell you a little bit about the last part, where we want to now introduce a new variable in the system that is going to constrain the mechanical equilibrium on the whole time. Because what I've shown you is that with this dissipative dynamics, we are producing stress, we are producing dislocations, but they're all slaved to the diffusive dynamics. In reality, when we deal with the real crystalline materials, the elastic stress relaxes much faster than any dissipative motion because you have the vibrations, and the vibrations are, typically die out. The elastic vibrations die out much faster than any diffusive process. So you would assume that there is a huge separation of timescale between the diffusive relaxation of the density field and the elastic perturbations. And how do we implement that? So this is an example where, can I show this? Yeah. Where we have the annihilation, that was quite quick, of a dipole. So you see it happens quite fast. Maybe I can show it to you again. Poof. And then there's still a lot of relaxation afterwards. But you already see that there's almost like a flow around it, like a honeycomb straw. This is very different than what happens in an actual crystal, where it's where you constrain the stress to be at elastic equilibrium at all times. So for this particular case, we can also extract the topological defects when they're in the same glide, and we can show that they're topological defects because we look at the amplitudes, and this is the Berger vector. So this is where we can calculate it and show that it's a very quantitative formula. So if we calculate if we make a cut through the 2D stress field along this plane, we see the profile of the stress field at various times. So we start with initial times, and then you see those two peaks coming together. That's because they annihilate, and eventually it's going to dissipate, and then it's going to take a long time before this bump is going to go down to zero and you have perfect equilibrium. This is for the case when we have just diffusive dynamics, and if we look at the stress away from a dislocation, in this case here, and you plot it in a log-log scale, you see that at the beginning you might have some sort of scale invariance because we start with the stress field induced by, when we put this to dislocations in the system. We don't let them come up. We know that the phase field is also able to produce topological defects, but then you have to do a different scenario. In this case, we just start with two dislocations, so we put them in as topological defects. That means we introduce a vortex in each of those phases, and we use the isotropic vortex approximation. That means that at the beginning, there is some sort of a scaling law in the tail here that comes from the, whatever approximation we use for the vortex. We know that the flow field away from a vortex goes as 1 over the distance, right? So the stress is going to be like 1 over r away from the vortex. So that's what we're going to see here too. But as a function of time, we see that this power law tail or whatever was in here, it disappears. We have crossing between the lines. So the self-similarity that we put in as an initial condition is not preserved by the model. And that's because the system is dissipative and it's not consistent with mechanical equilibrium. However, if we now constrain this mechanical stress, this elastic stress, to be at equilibrium at all times, and there's a little bit of technicalities involved numerically how you constrain this, because there's a huge separation of timescale. So on this diffusive, so we wanna evolve the psi field on this diffusive time scale with the constraint that at each time the stress field calculated, determined by this psi field, is at mechanical equilibrium. Yeah, but we have a scheme by which we can do this, and what we obtain is that when we do the same setup, the same initial condition, we see that in this case the power law with 1 over r predicted by the linear elasticity is very nicely preserved at all times. The dynamics is also very different and happens much faster. And in particularly, we see a huge difference when we look at the velocity of a dislocation. In this case, the dynamics of the dislocation is driven by the local stress, and the stress is induced by the other dislocation. So the fact that we have another dislocation, there is a stress acting on the second dislocation, right? So they move with respect to the internal stress generated by each other. So the velocity of one dislocation, in this case the motion is only glide, so that we only have the Vx component. So if you track the Vx as a function of the distance, we see that for different quenting depth, the green line shows you the 1 over r prediction from the linear elasticity, that the velocity is going to go as 1 over r. So they go faster and faster and faster towards the annihilation point. It's like a runaway behavior. And it's very far away from it. The deeper the quench, the more significant deviations we have. The lower the quenching depth, we see that at some point it does look like, so we start here, initially they're far apart, and then as a function of time, they're going to move closer to each other until the annihilation point, right? And initially we see that there is some sort of equilibration, and then it gets into a regime where it does look like they approach the analytical prediction. So that means that in the case where we're close to criticality, the mass diffusion is much faster, that it actually operates almost on the same scale as the mechanical equilibrium. So the stress is kind of relaxed on that time scale. But in the other situations, we see that this is a very different case. Whereas when we impose the mechanical equilibrium, there doesn't seem to be much dependence apart from the mobility being different, which makes sense that the mobility will be different in these cases. But the power law seems to hold for a range of quenching depth, which gives us confidence that this is a valid way in which we can impose mechanical equilibrium. Okay, so I think I'm going to stop here. So let me wrap it up by saying that we have taken a phenomenological model for crystalline material in the realm of this faithful crystal model as a base model for us to introduce a microscopic stress, which when averaged over the lattice units gives us a mesoscopic scale, a mesoscopic stress that can be used to study mechanical properties of crystalline matter, in particular when you have topological defects. And we have shown that in this framework in which we define defects as topological defects in the water parameter, we can calculate their motion, we can determine their location, we can determine their motion, and we can also constrain the interactions between them to be mediated by a stress that is maintained at equilibrium. With this, I'd like to thanks.
Thank you. So, time for questions, comments.
So the relation that you mentioned between lambda and A naught squared.
Yep, the Lamé coefficients and the.
Yeah.
Yeah.
Can you think of it as a fluctuation distribution? Lambda would be like a response function, and A naught would be like
That's we didn't think about it, but yes, I think so. I think so, because then you would relate something like the shear modulus. So one of those, a combination of the Lamé coefficients would give you the shear modulus, right? And you can relate the shear modulus with some sort of correlations in the density fluctuations. And if you average, then maybe it's going to. That's an interesting question. That's, I think it's, yeah, it could be related, but we didn't think about it in those terms. Yeah.
It's also related to doubts about the dissipation. At the very beginning, you were introducing a potential and noise. There was no friction, no dissipation at all. Only potential and noise. Then at some point, dissipation was in the discussion, and you missed when dissipation started.
Yes. So the fact is that the equation of motion of the particles had dissipation in them. It was a super damp motion, like Emilia was saying. So here, I said that it was satisfying the Newton's equation of motion. But that would mean that the acceleration is equal to damping, is equal to potential force, is equal to noise. And we're ignoring the acceleration and the inertia term, and so we say that the damping is equal to, yeah. And this is the reason why we have dissipation. Everything is so
then you cannot quantify the amount of dissipation in connection with the amount of noise.
You mean like a fluctuation dissipation?
Yes.
Well, I guess it's related to this this term here, to the diffusion constant, right? I'm not sure. What do you think? Because it's I mean, this is more in the spirit. This model is in the spirit, but it's not directly related to the microscale.
D is proportional to temperature, and the proportionality constant is the mobility, but is alpha, so you cannot extract this.
Well, the question is if this are really third colloidal particle close to thermal equilibrium, or is this something else that looks like if they're out of equilibrium systems. that still have a noise, but it's not necessarily thermal noise, then it's not obvious that you have a direct correspondence between the dissipation and the noise amplitude, right? So, yeah.
No questions?
I guess it's related to this. In the fixed model, you also you mentioned at some point the temperature about
the quenching depth.
Sorry?
Yeah, it's the temperature.
Movement, for instance, no?
Yeah,
Say,
yeah.
And what is the temperature in
The
that?
temperature in here is in the quenching depth, so it comes in this potential here. So the free energy has the local part and a non-local part. The local part has the elasticity, has the lattice periodicity, everything. The local part encapsulates all the temperature in the model, and the temperature gives us it's in this parameter, which it means how far away you are from the critical point. So epsilon in the Landau theory, it's approximately T minus Tc. So when epsilon is positive, you're above the critical point, it's just the liquid phase. When it's negative, you're below. And so it tells you how far away you are from the critical point.
Is that for the climbing motion of the defects, when you change spreading at some point, they attract also in the vertical direction?
Yeah, exactly. So exactly, that's exactly what happens. Maybe I should have shown the movie that you don't have annihilation in this case. If I start the simulation at very low quench, far away from the critical point, that means I have relatively cold crystal, I will see that it's going to take a very, very long time for these guys to actually annihilate. Basically, it's not going to happen. But if I start close to the critical point, so like a warm crystal, they're going to come together. They're going to annihilate, just as if when they are on the same light. Yeah. So it's different.
The question? I have one. I am lost on some part of the physics. The elasticity probably means something related to conservation of momentum. But you, from the beginning, from the starting equation, you are in an overdamped motion, so that you don't have conservation momentum. Momentum is lost by dissipation until you get to equilibrium.
That's why you need to introduce it again. So that's sort of the conceptual argument that we are having with each other.
The idea is that there will be some more fundamental model in which you have the stress field and the density field coupled in such a way that everything is conserved in the proper way. Now you gave a recipe. Okay, let's forget about the stress field, and just at every time step of the dissipative dynamics for the density, we readjust the stress infinitely fast, and then we come to the simulations. This is what you do. Is there any guarantee that this dynamics is some limit of the original dynamics? Or?
Yeah, it depends on how I tell the story, because if I say I just have this free energy, I don't know where it comes from, but I know that it gives me a pattern, so I just deal with this pattern, then I don't have the microscopic derivation. But if I say that this free energy comes from the density functional theory, and I actually have colloids, and I actually have particles on the microscale, then I would say that one could do a proper calculation with the hydrodynamics of these colloids, and actually coarse-grain the hydrodynamics, and find out exactly the correspondence between all of these quantities. And that's something that maybe we should do for this particular case, if we consider that this is a colloid that is constrained to behave like a solid material. Right? That could be like a limit. But we've already sort of started from the phase field crystal model where we just have this free energy. And there's been some papers where they show that this free energy has some relation to the density functional theory and colloidal solidification, but it's not the one-to-one correspondence. There's a lot of approximation. So it depends on where do we start? That's the phenomenological starting point. Where do you say that this is given? And from here on, we have things that we can predict.
More questions or any comment? If not, thank you, Luiza.
Thank you.
No, it's okay. Let's explain it for you. it goes from
It's
this.
the
This can be
entropy
derived
part,
from the,
yeah,
from the
exactly.
so algebra equation you can do.
Yeah,
Exactly, exactly this equation. Exactly, there's no possibility. The next slide is no possibility.
Yeah, so
You get this, well, you don't get that. I mean, you have lots of delta functions.
So there's a
multiplied by
diffusion
noise,
term
it's pretty
coming from
tricky.
here. There's a diffusion term coming
Yeah.
from this term. And the diffusion term can be written at the free energy level as a log. So it's an entropy, it's an entropic diffusion.
And this is then there is a problem because rho is a collection of deltas, and the logarithm of a collection of deltas, which is mostly zero. So that is not, in the mathematics, it's not very clear.
No.
But you do the maths and you write this formula.
Yeah,
And then,
because at the